5.7 is on rational exponents. So some of you guys have noticed the connection with this already, that things can be written with fractional exponents, but some of you guys are going to think this is new. Okay, so rational exponents are exponents in the form of a fraction, so m over n. N can't be 0, so you can't have like x to the 2 over 0. That doesn't happen. Okay. So if you have an exponent of 1 over n, it indicates the nth root. So we've talked about this before. I told you that if you wanted to put in like the 4th root of 81, right, you put it in as 81 raised to the 1/4, like that in your calculator. That's what we're doing. So where it says 81 to the 1/4, what that represents is the 4th root of 81. Which by this point, you guys know you can do your factor tree, 9 times 9, 3 times 3 times 3 times 3, so you end up getting 3. Okay, so you can also go the other way. You can start out with things that are radicals, and you can go to fractions. So if I have the cube root of x to the 6th, y to the 12th, it's going to be x to the 6 over 3, y to the 12 over 3. And that's what I was saying before. It's just division, right? So 6 divided by 3 is 2. Y to the 12 over 3 is going to be y to the 4. Just what we did last section. Just writing it as a fraction exponent. Okay, now if I have 9 to the 3 over 2, the top number, the m, is going to be your power. The bottom number is going to be the root. Okay, it makes sense because if I had like 9 to the 1/2, it's the square root of 9, right? So if I have 9 to the 3 over 2, it's going to be the square root of 9 raised to 3. So I didn't write it 2. Do you guys see where the 2 is? Right, the 2 is represented right here, like the square root of 9. Okay, so you don't have to draw that 2 if you don't want to. I prefer to write it this way instead of, like, some people write it like the square root of 9 cubed, and they put the cubed on the inside. I don't like that way because it's hard for me to think of 9 cubed in my head and then take the square root of it. It's much easier for me to do the square root part first and then raise it. Do you guys see what I'm saying? So like the square root of 9 is 3. So then 3 cubed gives me 27. So you can write it either way. So you could do like the square root of 9, all of it cubed, or the square root of 9 cubed. Okay, so this next one, I have the 5th root of x cubed. It's going to be x to the 3/5. Okay, so the next one is it says write the expression in radical form and simplify. So this is something that I typically put on the non-calculator portion of the test. Okay, because all of you guys can put in your calculator -32 raised to the parentheses 3/5, and you can get an answer. That's not what I'm looking for. I'm looking for you to be able to do it without a calculator. So I have the top number is a power, the bottom number is the root. So when I rewrite this, it's the 5th root of -32, and then it's all being raised to the 3. Don't write no solution. This is the 5th root. You can take the 5th root of a negative number. You get -2 cubed. So your answer is -8. So I want to see, like on the test, I want to see you write it in a radical form and then simplify it all the way down. Okay, the next one is 16 to the 3/4. So the top number is the power, the bottom number is the root. So I have the 4th root of 16, and I'm raising it to the 3. So 4th root of 16 is 2. 2 cubed is 8. The next one I have -9 to the 5 over 2. So this is -9 under a square root. Everything raised to the 5. What do I write? No real solution, exactly. So we're going to talk about imaginary numbers in 5.9. This would be an imaginary solution. All right, 100 to the 1/2. So yes, it can be hard when you have like a 1/2. I think a lot of people forget what the 1 represents. So it's like 100 to the 1 under a square root, right? That's what it's representing. So in other words, it's just the square root of 100. That's all I would write. Square root of 100 is 10. 243 to the 4/5. This is the 5th root of 243. And then it's raised to the 4th. Does anybody know the 5th root of 243?
4.
Nope.
5.
Nope. Smaller.
7. 3.
3. Yes, it is 3. And you could always do, like if you weren't sure, you could do your factor tree. You could say, oh, 3 and 81. 81 breaks into 9 and 9. 3 and 3 and 3 and there's 5 3s, right? So you can do it that way if you need to. I probably won't give you like a big number like that on your test. I don't want to like stress you out. So the 5th root of 243 is 3. So I have 3 to the 4th, which is 81. And the next one, negative 343 to the 1/3. So that's the cube root of negative 343. You know this one?
Wait, what was?
Negative 343?
4,
Nope.
5, 6.
7 is correct. Oh, first try over there. All right, Tyler, how did you know it was 7?
That was Emerson.
Oh, Emerson, how'd you know it was 7? You just guessed. First try. Yeah, one thing you can do is it's usually going to be a small number. So I always think about the end of the number. So when I do 7 times 7 in my head, 7 times 7 ends in a 9, right? 49. And then when I do 9 times another 7, that's going to end in a 3. So that would be my first guess. Like I wouldn't try like 5 because I know 5 times 5 ends in a 5. 5 times 5 ends in a 5. I wouldn't try 5. Yeah, so you can kind of, you can cheat your way through with cube roots, square roots, and so on. Or you can just memorize all of them, like I did. I didn't memorize all of them. I memorized every single square root and cube root in the entire world. No, I did not. But I know the basic one. All right, here we go. So let's go the other way. So let's put it from radical form and put it into rational form. So if I have the 8th root of 13 to the 4th, that's 13 to the 4/8. So remember, the top number is your power. The bottom number is the type of root that you have. You can reduce it. So you get 13 to the 1/2, which that could be your answer, or you could write it with a radical and you could say square root of 13. So it doesn't matter. I'll accept either one. Square root of 13 is probably the one you're most used to, right? All right, so this next one is going to be 3 to the 15 divided by 5. So 3 to the 3, which is, no, 27. Everybody always says 9 on that. All right, 27. The next one, 11 to the 6/3, which is 11 squared, which is 121. All right, now these ones are a little bit strange. So it says rational exponents have the same properties as integer exponents. So for instance, if I had like x squared times x to the 5th, we know that that's going to be x to the 7th. So the same idea here, we're going to add our exponents when we multiply things with the same base. So I have 7 to the x times 7 to the x. So I'm going to have 7 to the, and I'm going to add those, x plus x. So I have 7 to the 2x equals 7. Okay, what's really going to help us on these problems is if I write the right side as 7 to the 1st power. So I have 7 to a power equals 7 to the 1. Do you guys see that the 2x and the 1 have to be set equal to each other? They have to be the same thing. Otherwise, those things aren't going to be equal. So that's what we're going to do. So we're going to say 2x is equal to 1. So when we divide it out, we get x is equal to 1/2. So let's think about if that's true or not. So start back at the beginning. 7 to the 1/2 times 7 to the 1/2, is that equal to 7? 7 to the 1/2 is square root of 7 times square root of 7. That would be square root of 49. Is that 7? Yeah, it works. So it looks weird at first when you see 7 to the x times 7 to the x equals 7. You're like, what? How does that work? All right, so the next one. So I have 2 to the n times 2 to the n. So I have it, let's see, 5 times? So I have 2 to the 5n when I add them, add the powers. So I get 2 to the 5n equals 2. So like I did before, I'm going to write that as 2 to the 1. So that way I can set my powers equal to each other. So 5n has to equal 1 in order for those two sides of the equation to equal. So I get n equals 1/5. All right, this next one, I have 3 to the 7n over 5 times 3 to the 3n over 5. So I'm going to get 3 to the 10n over 5. I add my exponents. Equals 81. But this one's a little bit different because in the last examples, I always had 2 to a power equals 2 to a power, or 7 to a power equals 7 to a power. But now I have 3 to a power and I have 81. So what am I going to do? Yeah, Alex? Yeah, perfect. So you're going to rewrite 81 as 3 to the 4th. Right, that's what it is, 3 to the 4th. And the other side is 3 to the, it simplifies down to 2n, right? Or, yeah, 2n. So if 3 to the 2n equals 3 to the 4th, that's when you can set your two powers equal to each other. So you have to have the same base in order to do this. So I have 2n equals 4, so I get n equals 2. Okay, so we're going to be simplifying things that have radicals or rational exponents. And there's different rules. So things are fully simplified when it has no negative exponents. So just like before, we couldn't have x to the negative 2. We wrote that as 1 over x squared. It has no fractional exponents in the denominator, because if I had like 1 over x to the 1/2, what that represents is 1 over the square root of x, which we would then need to rationalize. We can't have square roots in the denominator. It's not a complex fraction. A complex fraction is something that looks like 1/2 divided by 3/4. It's like a fraction within a fraction. And the index of any remaining radical is as small as possible. So that kind of goes back to 2a, where we had the 8th root of 13 to the 4th. We reduced that and had 13 to the 4/8, which is 13 to the 1/2, so it was the same as square root of 13. So when they talk about the index, it's the little number there. So 8 could have been changed to 2. So the index is as small as possible. So that's kind of what they're talking about there. All right, so let's try simplifying. So simplify each expression. So number 1, I have 7 to the 7/9 times 7 to the 11/9. So I'm going to get 7 to the 18/9, which is 7 squared, which we know is 49. Okay, this next one you might want to write small. It's kind of a long one. Okay, I'm going to first write it with rational exponents. I'm going to write it as 16 to the 1/6 over 2 to the 1/3. But I can't subtract my exponents because I don't have the same base. I would need it to be like 2 and 2, right? Something like that. So what we notice is that 16 can be rewritten. 16 is 2 to the 4th. So I'm going to write it as 2 to the 4th raised to the 1/6 over 2 to the 1/3. So because I need them to be the same base. Kind of like when we first learned in section 5.1, like x to the 5th over x squared, you could say x to the 5 minus 2, or x cubed. These were the same base, right? You had x and x. That's the only reason you could do that. You wouldn't be able to combine something that was like that and just subtract your powers, because they don't have the same base. So that's kind of what we're doing here. They didn't have the same base. They were 2 and 16, so we need to change them so that they're the same. Okay, so now on the top, I have 2 to the 4th raised to the 1/6. So I'm going to multiply. So multiply here. So I'm going to have 2 to the 4/6. Can I just write that as 2/3? Are you guys good with that? This is 4/6, which is 2/3. So 2 to the 2/3 over 2 to the 1/3.
How do you do 2/3?
I did 4 times 1/6 and got 4/6. And then I just reduced it. Kind of like if I had x squared raised to the 4th, it's x to the 8th. That's what I did there. I just multiplied 4 times 1/6. 4 over 1 times 1/6, right? 4/6. All right, so then I subtract my powers. So I have 2 to the 2/3 minus 1/3. So I get 2 to the 1/3. You can leave your answer like that, or you can rewrite it. What's 2 to the 1/3? Alex? Cube root of 2. Exactly, either way. I'm fine with either one. All right, number 3. This one's a little bit easier because they do have the same base. So when they have the same base, you can just subtract the exponents. So you're going to have 16 to the 3/4 minus 5/4. So we get 16 to the negative 2/4, or 16 to the negative 1/2, right? Remember, a negative exponent means 1 over. So I'm going to have 1 over 16 to the 1/2, which is 1 over the square root of 16. So your answer is 1/4. So they go all the way down. All right, this next one's similar to what we were doing on in that last section, but we don't have the same bases. So see how I have 8, I have 2, and I have 16. We can change those so they're the same base. So they would all be 2 raised to something, right? So I'm going to change them. So that was my little hint, right? Using one base. So when you have 8, 8 is 2 cubed. So I have 2 cubed to the x. And then I have 2 to the 2x. And then I have 2 to the 4th. Okay? So I multiply. So I get 2 to the 3x times 2 to the 2x times 2 to the 4th, and then I add my powers. Nope. 2 to the 5x plus 4. 5x plus 4. Do you guys see it? Now the next one, number 5, you actually cannot get those to be the same base. Like 36 and 32, if you did like the factor trees for them, 36 has both 2's and 3's, but 32 only has 2's. You can't get them to be the same base. Like they're not both 2 to something or 6 to something or whatever. Okay, so we're going to do each one kind of individually. Okay, so let's start with the 36 to the 3 over 2. So let's write it with radicals so we can see what it's saying. So 36 under a square root, right? The bottom number was a 2. And then I'm going to raise to the 3. So 6 cubed. And then the next one is 32 to the negative 3/5. That's a negative exponent. So whenever you see a negative exponent, do 1 over. So then I'm thinking 32 to the positive 3/5 would be the 5th root of 32, and then raised to the 3. Okay, so the first one, 36, the square root of 36, yeah, I guess it was 6. You guys know 6 cubed? 2 something. 216. Yeah, you can always do it off to the side. 36 times 6, 216. All right, now the next one. You have the 5th root of 32. 2. And then raised to the 3. So I have 1 over 2 cubed, which is 8. So now I just multiply those together. You can think of it as 216 over 1. I like to reduce. Like I would think, oh, that goes in 108 and 4. Do it again, 2 and 54. 54 divided by 2 is 27. Like I would probably do it that way because I didn't really know like 216 divided by 8 off the top of my head. So I'd probably just keep reducing. So we get 27. All right, so same one on the next one. I'm going to do number 6 down here so I have a little bit more room. So I have 81 to the negative 1/2, and I'm dividing by, so I'm going to do the little obelisk sign, the old school division sign. 27 to the negative 2/3. Do you guys see why I decided to do that little division sign? Do you see you're going to have like a fraction divided by another fraction? Yeah, the first one, I mean, they're both a negative exponent, so they're 1 over something. So the first one is 1 over, I have 81 to the 1/2. Okay, so that's the square root of 81. And then I have divided by, yeah. Like as a fraction, you would do 1 over the square root of 81 divided by 1 over blah, blah, blah. Like you would just do a fraction within a fraction. That's what we call a complex fraction. Yeah, it's really, that's why we call it complex, right? Because you look at it and you're like, whoa, that looks messed up, as Alex said, right? All right, so the next one we're going to have divided by 27 to the negative 2/3. So I'm going to do 1 over because of the negative. And then 27 to the 2/3 is going to be the cube root of 27 raised to the 2. So the first one is just 1/9. We got that. Right, square root of 81, 9. What's the next one? It is 1/9. So 1/9 divided by 1/9? 1. That's your answer. So this answer is 1. All right, you guys try 7 and 8. Try 7 and 8. I'll come around. All right, here we go. So the first one, so I have the 6th root of 64, which I think all of you guys saw was 2. And then you have the 6th root of x to the 4th, which you're going to write as x to the 4/6. So then that reduces down, and that becomes 2x to the 2/3. You leave it like that. You can also write it in the root form. It'd be 2 cube root of x squared if you want. So that's what they mean by making the index as small as possible. We went from a 6th root and we reduced it down to a cube root. All right, the next one I have negative 8 to the negative 1/3. So the negative power means 1 over. So I'm going to have 1 over negative 8 to the positive 1/3. So cube root of negative 8. So you get 1 over negative 2. So negative 1/2. And this last one we first rewrite with roots. So square root of y plus 1 over the square root of y minus 1. But we have a square root in the denominator. So we're not allowed to have a square root in the denominator. So we rationalize. So what are we going to multiply by on the top and the bottom? I heard someone say it. Root y plus 1, right? So root y plus 1. Okay, so I'm going to have a numerator and denominator. The denominator ends up pretty nice. That's the whole reason we did this, because the outer and inner terms will cancel. So my first terms, when I FOIL, become square root of y times square root of y, which is y. The outer and inner cancel each other out, so like this one and this one. And then your last terms become negative 1 times 1, which is negative 1. So on the bottom, I just have y minus 1. But on the top, I have to FOIL, and I have square root of y times square root of y is y. Square root of y times 1 is square root of y. 1 times square root of y is square root of y. And 1 times 1 is 1. So I get y plus 2 square root of y plus 1 all over y minus 1. We leave it like that. Okay, and then the very last question is about weightlifting. So they found a formula. There's tons of formulas in the real world. Like you look at them and you're kind of like, what? Like, how did they get this? This is found with physics, this crazy formula. So m equals 512 minus 146,230 b to the negative 8/5. And it can be used to estimate the maximum total mass that a weightlifter of b kilograms can lift in 2 lifts combined. Okay, so have you guys seen this in the Olympics where they do like one lift and they put it down, and they do another one and they put it down? So usually, like, they're not always the same, like in both lifts, but it's like, I don't know, it's weird. So this person, Oscar Chaplin III, weighs 77 kilograms. That's going to be his mass, so that's B. That ends up being like 170 pounds if you convert it. So what is the maximum amount that he can lift in 2 lifts? So we're going to plug it in. So I'm going to have m equals 512 minus 146,230. B is 77, and I'm going to raise the negative 8/5. So when you raise it to the negative 8/5, what you do in your calculator is you do like a caret, let's go to caret, raised to the negative 8/5. Okay, you need parentheses. Unless your calculator uses what I call fancy type, and it lifts it up for you, and you can see it raised. Okay, so go ahead and do that really quickly. I got 371.831. Did you guys get that?
Yeah.
Okay, that's in kilograms. Okay, so it says his total in the 2000 Olympics was 335 kilograms. Compare this to the predicted value. So this is like a value that's found, that's the most that the human body can possibly lift if you are 77 kilograms. So imagine lifting and he's not able to lift, like his spine is going to collapse, right? That's like the max amount that he could possibly lift. He did 335. That's pretty darn close. Like 371 versus 335, really close. Really close. So let's see, how much are we off? 335 off by 36.831 kilograms. Okay, so we're going to convert our answer to pounds so you guys can see what it is, because I'm guessing a lot of you guys don't know kilograms. So if I have 371.831 kilograms and I convert it, I do my dimensional analysis or unit conversion, stoichiometry, whatever you call it. It was the last one that got you. I heard lots of I hate stoichiometry. That's another way to convert. Okay, so when you divide, you get 0.4536. Divide it out, I get 819.734 pounds. Yes, that's 2 lifts, but he's a beast. I can't even lift the bar, so I'm pretty impressed that someone can do over 400 pounds twice in a row. So that's crazy. All right, I can lift the bar, I promise. It's just not pretty.